All right, so concerning the homework assignment that we just submitted, I had some comments on some of your works, so I want to talk about what I meant. So in question number 1, can everybody see that and read? Or do I need to zoom in? All right, so hopefully we can see. Now here we just explain to find the PMF of the random variable X. It's a PMF because it is a discrete distribution. So for a discrete distribution, points have masses. Now the BDF. The BDF is for continuous random variables, and you count the number of possible results for X out of 5 cards. If you're picking, you have 13 cards, and you're picking out 5 cards, so you can't have more than 5 cards. So it's either 0, 1, 2, 3, 4, or 5. And for anything else, it's 0. And when you write that down, you need to remember that giving that PMF, you need to remember that the probability for everything else is equal to 0, right? Now, determine probability that X is less than or equal to 1 for a discrete random variable. That's the sum of everything that is less than 1. And in this case, it's 0 and 1. So you just add the 2. You can do the computations when you're doing that at home, not to waste time. If you can't, you just put the formula. And I do want people to use the...
So we could just give the formula and that would be okay.
Yeah. So, and I do accept that, but I do most of the time say, as you're doing it at home, it'd be good to see what the numbers are equal to, right? I don't take off points for not doing that. I was saying something. Well, okay, maybe later we'll come back. I was trying to say something and question came in. It's gone. All right. So this second problem is where almost everybody has a problem telling me what the CDF is equal to. It's good that you could explain all this. I think everybody got that right. The PMF to stop the experiment after X trials, you need to fail to have X minus 1 times, and failing every time you're failing, it's 5, 6. Because you have 5 sides of the die that are not 6, and those experiments are independent, so the probability of failing X minus 1 times is the product of the probability. That's the reason why you have that formula. You're multiplying the 5, 6, X minus 1 times, because the independent experiments, you fail, and independently of your result, you do it again. So that's like P of A and B and C and D and D, and they are all same with probability 5, 6. That's why the answer is 5, 6 to the power X minus 1. Then on the X trial, you get 6. That's why it's 1, 6. So you get this. And then remember that every other outcome has probability 0. Now, to show that the sum is equal to 1, that technically means what? Show that it's a probability distribution of function that you found, right? Sorry, a probability mass function that you found, not distribution, because we are talking about discrete random variable. So if you are accepting that these are probabilities, then you actually don't need to add these things, because if it's the probabilities, then the sum of all probabilities is equal to 1. Right? So this is like check your work. And so you write that. And then I change the variable here to start from 0 to infinity as the sum of geometric series starting at 0 is equal to 1 a over 1 minus r. The formula that's used here is this one, that sum k from 0 to infinity of a r to the power k equals a over 1 minus r when absolute value of r is less than 1. And that sum starts at 0. So that's what is used there to get that answer. And so you get 1/6 over, and r is 5/6 because it's the thing that is raised to the power k. So that's 1/6 over 1 minus 5/6. So you get 1. Now, in finding the probability of having an odd number, that's what this is about. And I define the odd number. The odd number is any x of the form 2 times k plus 1. K going from 0 to infinity. That's what an odd number is. Right? That's the formula for every odd number, 2k plus 1. So you are going to add these probability for all those values of k from 0 to infinity, thus taking all the odd numbers, and that's 5/6 to the power x minus 1. So here that's 2k plus 1 minus 1 times the 1/6. And that gives you k, sum k from 0 to infinity, 5/6 squared raised to the power k times 1/6. Again, this gives you right away a geometric series, sum starting from 0. The ratio is 5/6 squared, and then the coefficient is 1/6, so it's 1/6 over 1 minus 25/36. And then when you do that algebra, you get that the probability is 6/11. Now the last part is where I had the most problems with your answers. Remember that a CDF is defined for any real numbers. So when we define the CDF and you define f of x equals probability that capital X is less than or equal to little x, this little x here is a real number. Then you can just tell me that you plug in x here and add it up to x and you get 1 minus 5/6 to the power x. That's completely wrong, because x could be 1.5, 2.3, e, pi. I'm going to put pi here? No, that would be wrong. So you are adding up to the integer that is below x, not up to x. You are adding up to the integer that is below x. That is why to define f of x, you need to start by the integers that you have here. If your x is strictly less than 1, there is nothing that is less than 1. Your capital F of x is going to be 0. If x is between k, including k, and k plus 1, which is the next integer after k, then f of x will add everything up to k, not x, up to k. And therefore, that sum will give this. Huh? Zoom in. And this is a very important moment actually in that computation that you're doing. Remember that when you're dealing with a discrete random variable, your x that is in the CDF is still a real number. Though when you're adding over integers. So you need to make sure you always look at that integer that is right before x to put in your formula. Because again, I say, if you put the formula with x here, that means if I ask you, find example, capital F of E, what is it equal to? Is it 1 minus 5/5 to the E? No. How much is E? 2 point something, surely less than 3. So K in this case is 2. So that is going to be 1 minus 5/6 squared. Yeah. Okay. Any questions on this?
Oh, no, I have a question.
Yep.
So for the K, I understand that, you have to have a real integer, but how did you pick K and what does K stand for?
K is the integer that is right before x, and x is before k plus 1. So there is no other integer that is less than x, that is larger than k.
So we just assume that K is an integer, or do we need to write that somewhere?
We are not assuming. In all the definitions I'm using everywhere k as an integer in my work. So I don't need to be telling here that it's an integer.
Okay,
Everywhere k is an integer in my work.
I got it.
But your x that is in that definition, in the definition of the CDF, x is always a real number. Am I making sense now?
Yes, sir.
Okay. Most of the time, this is called the integer part of S, that K. If you want to use the language here, we could actually say that's 1 minus 5/6, so the integer part of X. Yeah. So just to tell you, that K is not just randomly there. That K is unique when you have X. You can't have two different values of K for any given X that you have. So it's a function of X, 1 to 1. Not 1 to 1, but it's a function of X. Right? To every X, there is only one K. But to many X's, you can have the same K, like 2.5, 2.6, 2.7 E, they are all having the same K. All right, next. When we zoom too much, it's hard to show. All right, so here we had find the CDF, and in all these examples, I just wanted to stress the difference between the continuous distribution and the discrete distribution. The previous example was a discrete distribution, how to handle X. And here, it's a continuous distribution, how to handle X. And the difficulty here relies on the fact that sometimes your continuous distribution can have a PDF that is 0 over certain intervals, and then you need to take that into account when you're defining the CDF. You need to give the CDF on separate intervals where where the PDF is defined. When the function changes, the form of the function changes, you know you need to split there and have a different formula for the other one. That's technically what I needed you to find out on this example. In the first one stated that you had f of x equal 3 times 1 minus x squared. Notice one thing, please, when you're solving a problem, if you find out that you have a negative PDF or PMF, get back and check your work. Because by definition, little f of x is always positive. Okay. So in your answer, you have a negative, check the work again. Now here, in this example, out of this interval, the PDF is 0. And the way it works, when you want to find the CDF, always start knowing that because it is for all real numbers, you start from negative infinity, looking for the values of the CDF, until you hit the change in the definition of the PDF. You will have one formula for the CDF. So if I start at negative infinity, from negative infinity to this 0, the PDF is equal to 0. So that's why I'm going to split at 0. So I'm splitting at 0. I say if x is less than 0, because of that reason, I'm going to have capital F of x equals 0 because I have not yet touched the support of the random variable. So capital F of x is 0. Now, on the interval from 0 to 1, I have a single formula for the PDF. So it makes sense to consider that the next interval. So if x is from 0 to 1, the CDF is just going to be the integral from 0 to x, because everywhere else it's 0. And this x being less than 1, it's okay. So we can integrate the whole thing. And you integrate that, you get this. When you plug in the number, that's where you end. 1 minus x cubed. Now, and then when you do this, you need to check your work always to make sure you're on the right path. If x is equal to 1, you know that here at this point, you have covered entirely the support of the random variable, right? The support of the random variable meaning all the set where the density is not equal to 0. You have covered it entirely. So you need to make sure that at this point, the value of the CDF is 1. If it's not 1, then you have a mistake somewhere. So right here, when I end this, the first thing that comes to my mind is, okay, when I plug in 1, what happens? 1 minus 1, 0 cubed, 1 minus 0, 1. Okay, so I'm fine. That's why when I'm doing this last part, I'm not even thinking. I already know the answer is going to be 1. Because what I'm getting when x is larger than 1 is capital F of 1. This is capital F of 1 computed from there. That's why I just write 1 minus 1 cubed, knowing it's 1. All right. And then after you finish your computations, please, you remember to write down the formula. That's the formula of F of x. It's not your computations. You finish computing, give the answer. It's the function that is defined on separate intervals, the way we have here 0 before 0, 1 minus x cubed between 0 and 1 when x is larger than 1. Now I changed the percentiles that were given in the homework just to compute others to see. So how do you define the percentiles? It's the number for a continuous random variable. You don't use the less than or equal and then larger, because you will have a point where that probability will be exactly equal to what you're looking for. So that's why for continuous random variables, you just write probability that x is less than or equal to q, in this case equal 0.25 for the 25th percentile, and you solve for q, which means take this q, plug into the formula of the CDF, which we have here, and solve for q. In that case, you solve for q, you get this. You do the same thing for the 60th, you solve for Q, and you get that. So I said, example B is similar to 1 because it's just one interval, so you do it the same way as for A. Now C was different from A and B. So I solved it separately just to have a density that is equal to 1/3 when X is between 0 and 1, and when X is between 2 and 4. Everywhere else, it's equal to 0. Technically, this means that it's a random variable that is uniform on the union of the two intervals from 0 to 1 and 2 to 4. Okay. Uniform meaning what? That all points have the same density. All intervals have the same chances of being hit no matter where they are, whether they are on the first segment or the second segment, doesn't matter. Now, same as before, we will go through the range, which is R, from -infinity to infinity. The way this is defined, you know, before you hit 0, your density is 0. So you start there. Capital F of X is 0 when you're below 0. Now, between 0 and 1, you must integrate from 0 to X. What? 1/3. That's what the density is there. When you integrate that, you get 1/3 of X. Now I check. This is what I was telling you about. At that very point of intersection, capital F is 1/3 F of 1. Then from 1 to 2, what happens? Between 1 and 2, the density is how much? Huh? Can I hear you? 0. The density is 0 between 1 and 2. So nothing is changing. So whatever was at 1 will remain till you get to 2, because there's nothing else that is being added. The density is 0. So for X between 1 and 2, capital F of X is equal to F of 1. That's why you put the answer. It's F of 1 because there's no density between the 2 points. So the function is going to, that means the function is going to be constant on that interval. Now, when you cross 2 and you continue towards 4, you have something else that comes in. But before that thing comes in, you already have 1/3 from that F of 1. So you have 1/3 plus the integral from that range where you're starting now to X. Why? Because integrating from -infinity to X is same as integrating from -infinity to 2, right? And integrating from -infinity to 2 is same as integrating from -infinity to 1, and it is 1/3. That's why you have 1/3. And then the second part of the integral from 2 to X, you just compute it. So you don't need to write those two integrals and compute them again if you already did the first part. That's the point I'm making here, okay? So you don't need to compute this thing again in that second part. So you just write that 1/3, and then you integrate from 2 to X, you get X minus 2 over 3 plus 1/3, which is X minus 1 over 3. And then you can check here as well. When you are reaching 4, when you reach 4, what's the value here? F of 4 equal 1, which is normal because 4 is the end of the support. After 4, the density is 0. So everything else there is going to be equal to 1. That's why for x larger than or equal to 4, f of x is equal to f of 4 because nothing else is changing. Therefore, that's 1. And then again, when you finish, make sure you put all of that in the definition of the function. And here also, I took time to compute the 25th percentile, the 60th percentile. And you can see how it works here. If I'm looking for the 25th percentile, I need to know if it's going to be before 1 or after 1, okay? Because there is a different formula for f of x on the intervals. Does that make sense? So I need to know whether it's here or it's going to be on top there. That's why I'm checking with f of 1 equal 1/3. 1/3 is 0.3, right? 3, and this is 0.25. It's less than, which means that the point I'm looking for is definitely less than 1. Therefore, I'm using the formula of f of x when x is less than 1. That's why. And so you get that it's 0.75, and 0.75 is definitely less than 1. So you are in agreement with the word. And then for the 60th percentile, you're looking for 0.6. And f of 2 is 1/3 also. And 1/3 is 0.33, which is less than 0.6, right? So that means that the point you're looking for is larger than 2. The point you're looking for has to be larger than 2. That's the reason why we are going to use this formula to find that. So we are not guessing, missing before going back to solve using another equation. We check like that. So here we solve using that formula because we already know that we are looking for a number that is larger than 2. And then we get that it's 2.8. And of course, it's okay because we were looking for something that is larger than 2. Questions on this one? Yeah. Graph of which one? I didn't put any of them here, but at the end, I'm going to put that for you. Anything else? Because we have issues with those graphs. Many people just, you know.
Will you go back up to A?
Okay, okay.
In the problem, it says 0 less than x less than 1. I was just curious as to why you put in the second line for 0 less than or equal. Like, how did you know that the equal would go on that line rather than the line above, just x less than or equal to 0?
It doesn't matter for continuous distributions.
Okay.
A continuous distribution, you know the probability that x is equal to a is equal to 0. So it doesn't matter what side you're putting or equal.
Okay, thank you.
And that's only for continuous distributions. Because like we say, I mean, who cares what one point is when things are continuous? Right? Probability of a point is 0. If you're disturbed by this point, remove it from here. End of the rest. It's not going to affect anything. Anything else?
Why do we have to use the 60th also? Because I know it's the book, which is the 25th.
Well, I said I did more than is written there. Just to explain what I was explaining to you here. How to choose what formula to use. If you were just doing the 25th, you will not know what I'm explaining, right? So here, technically, what I'm doing is not just giving you the answers to the homework. I'm actually using this as a teaching. I do more than just giving you the answers to the homework. Other questions? And what I'm saying is what is written here. This is more than requested in the problem. All right, so if no more question on this one, let's head to the next one. This next one, I think almost everybody got it right. So, but anyways, let's talk about it. So the PDF of X is given, and X is between -2 and 4, and it's equal to 0 elsewhere. And you're asked to find this, that, and this. Point to be made. This exercise had to be for you to remember the formula of the expected value of a linear combination, not to compute something here, there, and then write another integral again here to find the third one, because this third thing is a linear combination of the first two. So that was the point of the exercise. So we compute the first one, we compute the second one, and we use linearity to find the third one. So how do we do the first one? Integral from -infinity to infinity, but we are stuck on the range of X that is in the support. So we integrate from -2 to 4, X times X plus 2 over 18 dx. Now you do this any way you want, you get 2. Everybody got that one. So then you go expected value of X plus 2 cubed. So you get this, and this is where I go differently from some people. I don't open the parentheses, someone tried to. So that's X plus 2 cubed times X plus 2. That's X plus 2 to the 4th. And when you integrate, it becomes X plus 2 to the 5th over 5. And then you plug in the numbers 4 and -2, and so you get this. Now for the last one, you see that it is 6 expected value of X minus 2 expected value of X plus 2 cubed. And this you already know, it's 2. That one you know, it's 432 over 5. And you put them together, you get this one. Questions? Then we have the problem 1.88. There were some issues. So we have a random variable that has density. Again, this is PDF, f of x equal 2x between 0 and 1 and 0 elsewhere. Find the expected value of 1 over x. So it's an integral from -infinity to infinity of 1 over x, f of x dx. But the density is between 0 and 1. So we integrate from 0 to 1. Everything cancels, you get 2. So we are happy. We didn't have to find the distribution of the random variable 1 over x before finding the expected value. This is the point, right? We use the fact that the expected value of g of x is integral of g of x f of x dx. Now, the other way to find that expected value would be to first find the distribution of the random variable y that is equal to 1 over x, then use it to find the expected value, which is the second part of this problem. So the second part of this problem says, find the distribution of capital Y equals 1 over x. How do we do that? The CDF is equal to the probability under Y that Y is less than little y. Now it turns to the random variable x, because y is a function of x, probability that 1 over x is less than y. And then I want to flip here and say it's the probability on the x, that capital X is larger than or equal to 1 over y. But then I have a problem. Because if I want to flip those things, I better know that the y I'm putting in is positive. Otherwise, it changes things. And for that same reason, I have to find out what happens when y is negative. When y is negative, you got probability that 1 over x is less than 0. X is positive between 0 and 1, so no way 1 over capital X can be less than 0. So the probability is 0. Now, for y less than 1, 1 over y less than 1 of being positive, 1 over y is larger than 1. And probability that capital X is larger than 1 is 0 as well. Because capital X is between 0 and 1, right? Can't be larger than 1. That's why capital F of y is 0. So it's 0 all the way up to 1. And now if y is larger than 1, then 0 is less than 1 over y less than 1, and then I'm in the range of x. Therefore, it's going to be probability that capital X is larger than or equal to y, which is what I had here. And that's going to be integral from 1 over y, because x is larger than or equal to 1 over y, but we know that x is less than 1, right? That's why we integrate from 1 over y to 1, because x is less than 1. And that integral 2x gives you x squared, and then you have 1 and 1 over y, you plug them in, so you get that. And so you get the formula of the function that you were looking for. Before 1, it's 0. After 1, it's 1 minus 1 over y squared. And then you need to make sure, as I was saying, continuity. This function is continuity. It doesn't matter where I put 1, here or there. Check. Plug in 1 up here. 1 minus 1 over 1. 0, right? So it really doesn't matter where I'm putting or equal 1 here or there. It doesn't change anything, because the values of the probability are going to be same whether it's here or there. Then you take the limit when y goes to infinity. What should it be? 1. So when y goes to infinity, you get 1 over infinity, 0, 1 minus 0, 1. So yes, you think perhaps you got the right thing. Yes. Now, the last part of this question was use that PDF or the CDF that we found to find the expected value of y. And so to do that, you find the PDF, that's the PDF of y. How do you get the PDF? Take the derivative of the CDF with respect to y. When you take that derivative, you remember that it's 1 over. So when you're taking the derivative, there's a minus that is coming, and there was another minus there. That's why it's plus 2 over y cubed. And then y has to be larger than 1 and 0 elsewhere. So the expected value, because y is larger than 1, integral from 1 to infinity of y times the PDF of y. That's the definition of the expected value. And now you compute that integral, and you get that it's 2, the same 2 that we got here. So the lecture doesn't lie, perhaps. Right? Whether you use the PDF or you use the initial definition that was given, you end up with the same expected value. That's the point of the exercise. Any questions on this one? Again, that's what we got, the expected value here. That's expected value of y. Y is 1 over x. We got it 2. Now we got it here 2. Here we are using the definition of the expected value using the distribution of y. And here we are just using the theorem that was given that the expected value of g of x is equal to the integral of g of x, f of x, dx. In that first one, you don't need to find the distribution of y. And the second one, you need to find the distribution of y. Questions? Is everybody okay with me on this one? All right, so hopefully we are all okay and still friends. So we move to the next one. So the next and last problem of that homework was this one. I think some people had some issues figuring what goes where, but the most important thing in the statement of the problem, I think, is that we said that the PDF of f of x for some b that is strictly positive is going to be equal to 0 for every x that is larger than that b. And it's going to be 0 for every x that is less than 0. And those important points here, I would build the answer. And we want to show that the expected value of x is equal to the integral from 0 to b of 1 minus f of x dx. So you either start by this and you show that it's equal to that, or you start by this one and you show it's equal to that one. So I started from this and I showed it's equal to that. Please, warning, don't say this is equal to this to start your answer. If you're starting your answer by writing expected value equal that, if it is somehow at the end you still show that this thing is equal to that, there's something wrong in the thinking, because you started by accepting what you need to show. Am I making sense? So don't start by saying expected value of x equal that. You want to start by this and you want to call it something else, not expected value of x, because you want to establish the equality. So the expected value of x, by definition, it's the integral from negative infinity to infinity of x f of x dx. Because the support of f of x is between 0 and b, we can restrict the integral to the interval from 0 to b, because the density is 0 everywhere else. That's the reason. And now, this is integral from 0 to b of f, and this thing here is the derivative of capital F of x. Little f of x is the derivative of capital F of x. Now I say we integrate this by parts. Integration by parts states that integral of u dv equals uv minus integral of v du. So that's what we do, integrating by parts. So we get x, capital F of x, that's u dv, uv from 0 to b minus integral v, which is this, du. U is x, du is just dx. And now we plug in the numbers here. When we plug in the numbers here, we get b f of b. When we plug in 0, this turns to 0, and we keep that integral the way it is. So f of b equals 1 because f of x, little f of x, equals 0 when x is larger than b. That's the reason why f of b is equal to 1. So I use that here, and I get that this thing is b minus this integral. But b is nothing but integral from 0 to 1 of dx. So I combine that. It's integral from 0 to b of 1 minus f of x dx. That's it. Any questions? So if we have no questions, then I will start talking about the material of chapter 2. We are done with chapter 1, so congratulations to us. Chapter 1 is over. Now we know the basics of probability for one random variable, and then we are going to start bivariate random variables and everything that is related to it. Do you have any questions on that first part? There's a homework 3 that is already posted on Blackboard. Expected next week. There is a test next week.
Next week.
Uh-huh.
Next week is not 20.
Huh? Oh, so you know it's on the 20th. That's a good thing. Okay. Your homework is due next week, and you are supposed to do that, and then we come back here and talk about it the way we just did for this one, and you get prepared to have your test and the day that and the week that is coming.
Well, how do we know that B is integral without superscript?
What?
How do we know that B is integral without superscript?
Is it wrong?
I don't know. I'm just asking.
No, I'm just asking, is this wrong, that integral of dx?
How?
What is the integral of dx? What's the integral of dx equal to?
It makes more sense if
B.
you put a 1 in there.
Oh, B.
No. Let's go step by step. When you integrate dx, what do you get?
X and now
X.
minus 0.
And then you bring in 0 anyway. And so the whole point is you need to know where you're going, right? Because the things that you bring in this, it only works because I know that I want a 1 dx. I need to get a 1 there to complete the work that I was doing. Otherwise, it's going to be a waste of time. Most of the time in the proofs, what works because you know why you are using it. You know where you're going with it. If you don't know ahead of time where you're going with it, it's not that easy. So what most of you did was backwards. Start from this to show that it's equal to that. That is correct as well. So if you go this way, you do integration by parts right away from this one, and you work backwards to show that it's equal to that one. And I think I had one person who didn't go from one to another, took this one, did the computations all the way down to this, then took this one, did the computations all the way down to that. And if the two things are equal, then the beginnings are equal. It's also correct. So as long as you don't use any illegal transitions, if you if you manage to show that the two things are equal, then they're equal. Okay. Huh? Are we good on this one? All right, so there's something else that I would love to talk about here, but let us keep it where it is. And just talk about the bivariate random variables so that we don't get lost next time we start talking about it. All right, I'm happy if you are happy with this homework. Your test 1 will be homework 1, 2, 3. So you take the 3 homework materials to review for the test. Don't ask me for extra problem. Don't ask me for sample test. I never do sample test. I give you the homework problems. I provide the answers, and I say, use your homework problems to review for the test. I'm not going to take problems from math to give you. The problems are going to be similar to the ones that you have faced on your homework problems. If you did them by yourself and correctly on the test, you guaranteed to have your A, and that's it. Which is why even when you miss a problem on the homework, don't stop at that. Keep trying to understand what the answer was and why. And also don't be too worried about not doing one or two problems on the homework, because in the end, we have more homework problems than necessary to get 100. So actually, when you have a 21 or 20 or 19 out of 25, it doesn't mean that you lost 6 points out of 100. It doesn't mean that. You have maybe 10, 14 homework assignments when you know that all of them are worth 100 points. So having 6 points less than one doesn't mean that you have a bad grade on the homework. All right, so somewhere. Distributions of bivariate. So distributions of bivariate random variables. Bivariate meaning what? That you have a random variable that is actually a vector, either xy or x1, x2. So be the outcome of our experiment. Remember that everything that we do in this class is based on the outcomes of an experiment that we have, right? X1 of C, X2 of C. Now we know what a random variable is. It's a function that is defined on the outcomes of a random experiment as defined earlier. And see X equals X1, X2. So you want to find the distribution of x1, x2 as a vector would be finding this probability that the vector x1 is less than the little x1 and x2 is less than the little x2. For a discrete random variable, we have a joint PMF of x1, x2, and for it continuous random variable, joint PDF. Let's say we do have, if we assume that X has values, let's say A1, A2, A3, and B, so that's X1, X2 has values B1, B2, B3. If we assume that X1 has values A1, A2, A3, and X2 has values B1, B2, B3, then it is convenient this is for a discrete, right? That's a discrete random variable. To use the table before here, not to think that they are always same for the joint PMF of X1, X2. So here we can draw that table. And then you put their values here, B1, B2, B3, B4, A1, A2, A3. So here we have the variable X1, and along that line we have the variable X2. So it's convenient to do this. And then here you are going to put the probabilities of the outcome A1, B1. So this is P of A1, B1, P of A1, B2, and so on. Okay. So inside the table, you put the probabilities that X is A1 and B and X2 is B1. Here you put probability that X1 is A2 and X2 is B1 and so on. You put all of that. And then I always put an extra column here, an extra row here for what we are going to talk about next. The extra column, at the intersection of the extra columns here, you need to always check that things add up to 1. Meaning what? Everything that I put inside this table, excluding this row and that table, everything that is inside that table must add up to 1 because it's a probability distribution function. So the sum of probabilities of all possible pairs is equal to 1. And that 1 is reflected here when you draw that table. You make sure that you get that 1. Also, when you have that joint distribution, I recommend that you add everything that is on this row. You put here, sum 1. Everything on that row, you put it here, sum 2. Everything on the third row, you put it here, sum 3. And guess what? The sum of these must also be equal to 1. A new word right here. Often you will hear that question from me. And if you draw this, you answer all your questions on this little thing without having to do anything else. Check here. New word, marginal distribution. So what you get here is marginal distribution of x1, which means what? That right here is probability that x1 equal a1. This here is probability that x1 equal a2. And that here is probability that x1 equals a3. And this is the reason why when you add all of them, you get 1, because this is a distribution function. And the sum of all probabilities must always be equal to 1. So the sum of the probabilities for x1 must be 1. That's why the sum of this column must be 1. So when x1 is going as a column, the column of the sums that you're adding gives you the distribution of x, which we call the marginal distribution of x because it is given independently of x2. There is no x2 here. We have removed that effect of x2 and we're just looking for the probabilities for x1. That's why we call it a marginal distribution. It concerns only x. It doesn't concern x2. It concerns only x1. Second, I say you take this second one, you add everything here, and you put here. Add that column, add this column, put here. Add that column, put here. Add these column, put there. Now you can guess what is going to be this column, this row. Huh? The sum must be equal to 1. And what does the row represent? Marginal distribution of x2. That's it. So what you get here is marginal distribution of x2.
Hey, Dr. Longlet, so this is just a two-way frequency table?
No. That's very far from here. So on this row, and technically you could actually say that two-way frequency table is an application of this. You do the two-way frequency table because this is true. Okay. Now here we're saying you have the marginal distribution of x2 by adding the columns. Notice that here you got distribution of x2, but there is x1, right? You got distribution of x1, but here is x2. So be very careful with that. So right here, you get probability that x2 equal b1, and so on. Any questions? Do we have any questions about this? Now, when you have a continuous random variable, it's a completely different game. So, for a continuous random variable, we have f x1, x2 has joint density. Joint PDF. And the marginal distributions are obtained via integration. So you need to take the integral over the entire range of the other variable. Meaning what? Meaning that little fx1 of x1 is integral from negative infinity to infinity of f of x1, x2, dx2. And then the marginal distribution of x2 is the integral from negative infinity to infinity of f of x1, x2, dx1. So if you integrate the joint density with respect to x1, you get the marginal distribution of x2. If you integrate with respect to x2, you get the marginal distribution of x1. But for a discrete random variable, what you need to do is the sums that I showed you on this graph. And that's it. It seems like it's showing me 45 here or 46. Any questions or any closing arguments before the jury goes for deliberations? Thank you. If that is no, I'll see you on Wednesday. Oh,
Dr. Marshall, it's Wednesday.
I mean, for me, this is really Monday. Sorry, guys. Yesterday, I'm completely messed up. I drove like 10 hours yesterday, and then I had about 4 hours delay because my tires got punctured on the way going 75 miles per hour. And I had to wait for 4 hours to fix them before I continue. So,
Where did you go, Dr. Marshall?
what?
I said,
I
where
was,
did you go?